Okay, good morning. So I will basically rely on a very nice and comprehensive overview by Susan and narrow down the topic to a statistical signature of interstellar turbulence in dust polarization maps. So from Planck measurements, this is public release 3 data, and there is an associated paper published in Astronomy and Astrophysics 2020. So these are measurements at 353 gigahertz, and they are done in like 70% roughly of the sky, excluding the galactic plane part. So these measurements allow us to have some quantitative information about the spectra of E and B modes, and also TE cross correlation. Okay, and so the question I am asking is very simple. Can we reproduce those observed correlations with very simple simulations of multi-phase turbulence? So and it's kind of a computer experiment that you just offer. So we have been working in star formation, right? Trying to reproduce this multi-scale process of turbulent stimulated star formation. So you start with gas in a thin layer in the galactic disk, and then you continue, and then you narrow down your simulations to 200 parsecs, roughly the scale height of the disk of the gas in the disk, and then you can zoom in further to filamentary structures that produce your young stellar objects in this context. But we are not going here today far towards small scales. We are just looking at multi-phase boxes of roughly the size of the scale height of the disk, okay? And so we will ask the simple question, so can we reproduce some of the observed, measured Planck spectra with this very simple-minded modeling? So I will talk about 4 different sorts of multi-phase turbulence models. So we have different resolutions, 512 cubed, 1024 cubed, and 2000 cubed. The box sizes are roughly the same, 200 to 250 parsecs. We use different mean densities of H1 in the box, which are 5, to mimic something that would be happening in the spiral density wave of the Milky Way. And we then go down to 1, which is the average density at the solar radius. We vary the RMS velocities in the box, but roughly in the range from 16 to 20 kilometers per second, which is what we observe essentially. And then we use different assumptions about the mean field, B0, which is close to 10 microgauss in A model, in case A. It's about 3 microgauss in case B to basically limit the range of possible effects of the mean field. And then cases C and D use similar B values, which correspond to roughly what is measured in the solar circle. We use different artificial forcing, which the first 2 models use solenoidal, fixed acceleration forcing, very simple one at large scales. The last model uses solenoidal stochastic Ornstein-Uhlenbeck model, also at large scales. And the case in the middle, actually simulated by Paolo Padoan and his collaborators, uses supernova feedback forcing in the box. So with this forcing, we get different Mach number regimes. So our sonic Mach numbers are in between 5, 5.4, 3.4 in the solenoidally driven models. And with supernova feedback, there are huge oscillations of the sonic Mach number in response to new explosions in the box. Similar picture can be seen in the Alfvénic Mach number regimes. So they are subalfvénic, 0.5, 0.7, 0.4 in the solenoidally driven models, and they are jumping from 1 to 7 in superalfvénic regime with supernova feedback. So, so the new simulation, the 2000 cubed one, is done at Los Alamos by Kavli and Kahoyuan, who are present here. Let's see, okay. So this is just to show what is going on in a thick slab in the box. And so you see a variety of filamentary structures forming with, in response to solenoidal driving. And then we pick a trivial dust emission model so that we can compute the intensity and Stokes parameters using these simple approximations. And so we rely on, we assume that polarized radiation of the dust is optically thin at relevant wavelengths, that dust-to-gas ratio is constant, and that grain alignment properties do not depend on density. We also use, of course, because it's a periodic box, we use flat sky approximation. So using this simple algebra, we can build synthetic dust polarization maps. So this is the one for case A. And you see the texture, which shows plane of sky magnetic field. You see black vectors, which show polarization pseudovectors. And then color represents H1 column density. So you see what you get from this map is that the column density range is roughly 1.5 decade here at this resolution. And so you can then, so this projection in particular, in this case, the mean field is aligned with the x-axis, and so you can see that the magnetic field texture goes roughly aligned with this direction, because the mean field is rather strong in this case, 10 microgauss. In a different projection along the mean field line direction, you see a slightly different morphology. You can follow roughly perpendicular polarization vectors with respect to the plane of sky magnetic field. Okay, so then we are interested in looking at how different spectra measured in these polarization maps scale and what kind of asymmetry between E and B modes do we see in these simple models. And so if you, because we know how numerics works, this resolution we are not resolving nicely the high density clumps in this multi-phase medium. We also don't resolve the time scale for cooling, so the clumps are not really physically correct in this modeling. So we mask out tiny fraction of the voxels in the box when we compute this power spectra. And so this mask is applied in such a way that all voxels with the density larger than 20 times the mean are removed from the map when we compute the map. And so we see that with this masking, we get E to B modes ratios slightly lower than the value observed by Planck, which is showed by the dashed line. And we get somewhat shallower spectral slope for the B mode spectra. Okay, so if we continue to masking with a lower threshold density, which is now 14 times the mean density in the box, we can actually reach the asymmetry values observed with Planck in certain narrow range of this spectrum, where we are supposed to see some feature corresponding to the inertial range. And then if we go even further and increase the threshold density to 10 times the mean density, then we see that the spectral slopes become steeper and closer to what is measured by Planck. And the asymmetry becomes also larger. So in this plot, the red line shows results for the projection along the mean field, and the other colors show perpendicular directions. Okay, and so because the mean field is strong in this case, you see that the spectra, the red spectra, differ quite a bit from the other two. So we see that this asymmetry depends on the orientation of the mean field in the box. If we look at the same result for model B, which has a mean field of 3 microgauss, with the same kind of masking, we can see that it is harder to reproduce the same asymmetry, although it's pretty close to 1.7, I think. In this case, the observed value is 1.92. And you also see that there is less of anisotropy in the box. So, for example, in the top spectrum of B modes, all three lines go basically on top of each other. So we can now look at what happens with when you do supernova driving. And let me run this short movie again. You can see by eye that the nature of structures that are produced in this simulation is quite different. And you can also see that the spectra look quite different, and asymmetry nearly vanishes, even though we are using masking. So this means that the energy injection with supernovae is changing the turbulence, and so we see nice slope of the B spectrum, again close to the Planck values, but the asymmetry is basically gone. It's at the level of 1.3 roughly instead of 1.5. 1.9. So when you look at the evolution of this spectrum, you can see that it jumps up and down, but never reaches the observed asymmetry. Okay. So now, what can we do with higher resolution simulations? So we expect better resolved dense structures. And so here, this movie shows you the the dense filaments that we see at high resolution, basically. Okay, so now we will be more quantitative. We don't need to do so much masking, and we can really ask physics questions about the origin of this statistical signature of ISM turbulence. So here we have the range of column densities of 2 decades roughly, and you don't see much in this picture because resolution is so high that the vectors are tiny. You can zoom in, but I don't have time for that. So this projection, this synthetic dust polarization map is built again for the projection parallel to the mean field in the box, okay? So we do the same kind of approach, but now we go more quantitative. So we measure the slope of the power spectrum of the B modes in this gray area, in the range of wave numbers, corresponding roughly to where we expect the inertial range in the simulations. And so we get the slope of -2.4 roughly, which is close to the Planck PR3 measurement, -2.5, okay? Also, when we measure the asymmetry, so this line in the lower plot shows the approximation for the red line, which is projection along the field lines, mean field line. So we get 1.9, and Planck measurement is also very close to that. It's also 1.9. The other projections give slightly different values, but they look pretty good. And also notice that now the threshold density to get this is just 40 times, okay, times the mean density in the box. So when we mask, actually we cut the tails of the distribution of the plane of sky magnetic field. We cut the very long tails, and you can see that the mask of 40 is somewhere in between the brown and yellow lines. So this is how much we cut, but you can see that this the fraction of voxels with this is very tiny. We can look at the TE cost spectra also in the simulation, and we get the slope of -2.4, while the Planck measurement is -2.5. We also get the level of TE with respect to EE spectrum at the right spot with polarization fraction of 0.33, 1/3 roughly. We can also compute the TE ratio, RTE, which Planck measured as 0.375. We get 0.264, roughly the same ballpark, but maybe a higher resolution would help to make it better fit. And this is the polarization fraction PDF that we built from simulations. This is the below, the bottom plot, and the top plot shows Planck results. And so to build this PDF, we use the polarization fraction of 1/3, which we get from the TE spectra. So here is my summary. So our simulations yield EE, BB, and TE spectral slopes that are observed roughly, and also EB asymmetry and TE ratios as measured by Planck PR3. So I think the measurements are reproduced in simulations, and now we can discuss why, how can we interpret this result. Thank you.
Thank you. Thanks, Alexei, for a very interesting talk. I ask the audience here is for questions. I have a first question here. When you say you clip, could that actually be a problem with the Planck measurements themselves that actually don't capture the extreme values of the PDF?
Oh, yeah, this is also possible, I think, yeah. But I think simulations have certain defects, and everyone who does simulations, I think, knows that.
Yes. What do the experts say on that?
Yeah, I would say it is true that on the very large scales and in the relatively diffuse measure region of the sky where Planck has made the best constraints on this, and again, very large scales, right? We're talking degree angular scale or greater, and masking out the galactic plane. So it's true that that's in a regime that both scale-wise and density-wise, you wouldn't expect to see these very tiny high-density structures. You also wouldn't, in general, get to the column densities of those first simulations really generically at all. What we should really, as a field, try to measure that would be a more closely associated measurement that we could compare to these particular simulations is high angular resolution, far infrared polarization towards small regions of sky. So really what you want are to go up to closer to a terahertz to measure small patches of the sky, really high angular resolution, and to do that in different environments, right? So we need a far infrared polarimeter in space or on a balloon.
Yeah, I agree. This is perfect suggestion. And I think in simulations, we also, I didn't talk about it, but we ran more models with different parameters, and we've seen differences with respect to what you get. So for example, the shape of the polarization fraction PDF changes in response to the change in the model parameters. But the modeling is very simple. There are 3 parameters to change. So.
Thank you. Elliot, next question.
Is your interpretation that the supernova driving model yields different results because it's much more compressible, or what's the physical difference?
This is a good topic for discussion. I think one difficulty with this model is that it lacks the large-scale forcing, which comes from the differential rotation of the disk. And so it's kind of, it's a nice model, but it doesn't capture the forcing in the disk. This is one thing. The other thing is that supernova driving is a big challenge for numerics. And so what you get by seeding supernovae somehow correlated with your density field, and then boom, exploding this stuff, is very difficult. So your method needs to be more diffusive to capture this, to ensure numerical stability. And so this aspect results in very fragmented structures in the volume, as you have seen. And so there are numerical aspects to this, which we want to expose, I think, because that would help us to move forward.
That's to be discussed further. Roger, next question, please.
Okay, thank you. A fascinating and dynamic interchange between theory and observation in all the talks this morning. It's been great. Thanks very much. I'm just trying to get my head around finding out how far both observationally and, in terms of simulations, your horizon is. How far, if you're looking at high galactic latitude, how far through the galactic disk are you actually looking, do you think, or do you envisage looking? Most of your signal is obviously coming from relatively local, but how far could you imagine going, say, way out into the thick disk and into the halo and so on?
Oh, for that purpose, you need to run different simulations, which are like simulating a column. Mm-hmm. I think that we are not ready yet technically because it requires a lot of resources to resolve all the relevant structures. If you want to model turbulence in such a big box, you really need a very high resolution. So there have been models like this computed, but the resolution is not sufficient to capture MHD correctly, I think.
Right. And in observation, you presumably have to use other measurements like, you know, Faraday rotation and so on to get to doing that. Okay, thanks.
Thank you.
Thank you. And maybe you are not even having enough depth in your simulation necessarily if you're really envisaging high galactic latitudes.
Yeah, this model are very simple, and that's what it is. So we cannot.
Susan, please.
Yeah, I'm curious if you could comment on the scale dependence of the EB asymmetry in the simulations. This is one thing that is not measured in Planck observations is a real change as a function of angular scale. And I notice you have a gray band on each of these plots. Is that what determined where you put that?
This is just where we measure the slopes and everything and the asymmetry. Everything to the right is affected by numerical diffusion, and so it's just technology.
Okay, so
everything to the left is the forcing, which is also technology.
Right.
And what is in between, what is left in between, is not so much. So we need of course naturally higher resolution modeling of this sort, and then we can get rid of masking completely.
Yeah.
I think, and we will know better what is going on in the gray area.
Yeah,
in the middle. Yes.
Yeah, I think that's really important. And another interesting comparison, because of course the observations have not just angular scale on the sky, but they're integrated across some depth in the real ISM. What's also interesting is that synchrotron observations show a different, more extreme asymmetry, and that is presumably related to the different line of sight weighting you're getting by probing a more homogeneous medium. So I'm curious if you thought about that too.
That's another direction we plan. So we want to do the same very basic series of experiments with synchrotron to see what is turbulence doing there.
Which is something that Susan didn't even mention much in your talk, right? Synchrotron emission. A lot more to be discussed. We will do that after the break during the discussion. So thanks first of all, Alexei.
Thank you.